Hey everybody, I wanted to take a really quick minute to make a video with a little more info about amino acid structures and pKa's. So have this information in one place to aid you with your studying. So again, a really quick recap of a generic amino acid. You looked at the pKa table in the book, you saw that every amino acid has a slightly different value for the pKa for their ammonium group and their carboxylate group. But for the purposes of this class, when you're trying to estimate the charge or figure out the protonation state of these groups at a given pH, we're going to make the assumption that the average pKa for an ammonium or an amine group is 9.5, and the average pKa of the carboxylic acid group is a pKa of 2. Now, one question that a lot of people asked about in class, and something that's going to continually come up, especially through the first exam, but you'll periodically have to whip out later on in the semester, is how do I know whether or not that group is charged at the pH that you want me to write the amino acid at? And so I'll take a minute to remind you, when we talked about buffers, we looked at the Henderson-Hasselbalch equation, and we had pH is equal to pKa plus the log of A minus over HA. And one thing you noticed is that if the pH was greater than the pKa, if we looked at the ratio of A minus to HA, this meant that the A minus was larger and the HA was smaller. So if we are at a pH greater than pKa, the conjugate base, or the deprotonated form, was favored. Similarly, if we have the pH is less than the pKa, this meant that the ratio of the log of A minus to HA would be smaller, and this would come from the amount of HA being larger and then the amount of A minus going down. So at pH less than pKa, the acid form, or the protonated form, is favored. We want to do that in a timeline. This is something that you might want to write out when you're doing a problem, is if we have pH equals pKa. If we're at pH less than pKa, the protonated form is favored. And if we're at pH greater than pKa, so let's say this is 0 and this is 14, we're at pH greater than the pKa, the deprotonated form. Now you may be wondering why I'm talking about why I say the protonated and the deprotonated form, or the acid form and the conjugated base form, instead of talking about signs, plus or minus. That's because depending on the nature of the amino acid, the sign of the protonated and the deprotonated form will change. And one quick note, if you want to remember how to write the ammonium, if you get stuck in a pinch and you can't remember the formalism, one way you can help is to remember that a physiological pH, an amino acid is a zwitterion, which means it has both a positive and a negative charge, and you can use that to help you remind you which is which. If you can always remember that an amino acid backbone is a zwitterion, and the amine is positive and the carboxylate is negative at pH 7.4, you can use that as an orientation point or a compass to help bring you back to that spectrum. Okay, so the first grouping of amino acids is relatively straightforward. These are the nonpolar aliphatic amino acids. So these are the amino acids that don't have a side chain pKa. And we're not really worried about them because they don't have ionizable protons, so they're kind of just there, and you really only have to worry about the amine or the carboxylate if they're alone in isolation, or if they're on the end of the peptide, they're having to calculate the charge or the pi for. One exception that's kind of funny in the nonpolar amino acid group is proline, because proline doesn't have a primary amine, so all amino acids, they have an N attached to the R group. So the R group being the C alpha and everything else that comes off it. And then they have 2 or 3, depending, amines, protons. And so because they're only attached to one R, it's a primary amine. But proline is different because the amine in proline is a secondary amine because it's attached to 2 carbons. And this actually makes it an amino rather than an amino acid. Now, things get a little funky with the aromatic side chains. So these are side chains that are aromatic, that have aromatic rings. And so phenylalanine and tryptophan don't have ionizable protons, although this group on tryptophan can be involved in hydrogen bonding for sure. But the exception is tyrosine. Tyrosine has a pKa of about 10.1. And so with tyrosine, if we have, it has a pKa of 10.1, you'll notice with tyrosine in the deprotonated form, it's neutral. And so if we're to look at pH of 10.1, tyrosine is going to be, and that squiggle is just an abbreviation that we're getting lazy and not drawing the rest of the molecule. Below pH 10.1, tyrosine is protonated, but above 10.1, tyrosine is deprotonated and carries a negative charge. So in that regard, it's going to look more like, even though tyrosine has a really high pKa, it's going to look and act like the other acidic side chains that we'll see in a minute. And again, some proteins possess the ability to sometimes tweak the environment around the amino acid to bring down that pKa. So sometimes you may see a tyrosine deprotonated at physiological pH. It just depends, but it's very rare. Things also get kind of interesting with polar uncharged side chains. So again, these are our side chains that have heteroatoms, so they're polar, so they have carbon connected to oxygens and nitrogens, but only one of these groups actually has an ionizable pKa. I know it's really tempting to take serine, glutamine, and asparagine and try to make them lose a proton, but they're not going to. The one exception is cysteine. Cysteine has a pKa of 8.2. So that means with cysteine, again, below the pH of 8.2, so at physiological pH usually, it's going to be deprotonated and be neutral, or protonated and neutral, but above a pK of 8.2, it'll carry a negative charge. So again, this is going to look a lot like the next set of amino acids that we'll see, which are our charged side. Okay, so these are amino acids that they're called our charged side chains because they're charged at pH 4 or pH 7.4 or physiological pH. So the other amino acids, they have the ability, so cysteine and tyrosine have the ability to carry a charge, but because of where they're at their pKa, they're neutral under normal conditions. Not so with our charged side chains. And so we have our amino acids that are negatively charged and are positively charged. We sometimes hear these referred to as acidic, and this is because they've already donated their proton. So they've already acted as a Bronsted acid and donated their proton. And so both of these guys, below their pKa, so if we have a pKa, so 3.6 here, we go out to 14, we go down to 0. At a pH of greater than 3.6, or 4.2 for glutamic acid, these guys are going to be deprotonated. But if you go below their pKa, they'll be neutral. So again, they look a lot like tyrosine and cysteine in terms of when they're above their pKa, they're negatively charged. When they're below their pKa, they're neutral. It's just that the pKas of aspartic acid and glutamic acid are so much lower that they're negatively charged at physiological pH. And again, we can call them acidic because they've already donated their proton into the media at pH 7.4. Now, the other type of amino acids are our amino acids that are positively charged. And again, we call them positively charged because they're generally positively charged at physiological pH. And these are lysine and arginine. And so lysine and arginine, you can see this is in the same ballpark as tyrosine for lysine, and arginine's 12.5. So these two are going to almost always be protonated at physiological 7.4. Okay? And so we can also call these side chains basic, and that's because they fulfill the role of a Bronsted base, and that they've accepted a proton and become positively charged at pH 7.4. And again, what makes these amino acids different than the ones we've looked at before is that we're still protonated. Below the pKa and deprotonated above pH equals pKa. But the difference is when they're protonated, they carry a positive charge, and when they're deprotonated, they're neutral. And so that's the case with lysine and arginine. And they both have, again, those really high pKa's. But histidine is kind of weird, because if we were to look at histidine and pH equals pKa at 6, physiological pH falls at 7.4. But if you do the math, the A minus to HA ratio is still around like 1 to somewhere around like 1 to 20. So the fact that even though histidine, the dominant species when pH equals pKa is the conjugate base form, and it's usually deprotonated and carrying a neutral charge at pH 7, the protonated and positive form still is around a physiological pH. It's just a lot less. And we talked about that a little bit in class. So just a quick reminder, and go back up to here. Oh, okay. So for lysine, arginine, and histidine, if we have pH equals pKa, when it's protonated, it carries a positive charge. When it's deprotonated, it carries a neutral. But out of these, only lysine and arginine are typically protonated at pH 7.4. For our other amino acids, so cysteine, tyrosine, and then aspartate or aspartic acid, glutamate or glutamic acid, when we're at pH equals pKa, when we're below and we're majority protonated, we're carrying a neutral charge or 0, and then when we're above pKa, we're carrying a negative charge for the deprotonated form. But only aspartate and glutamate are consistently and have a large population of deprotonated at 7.4. These guys are a little bit higher. And again, remember, we're talking about protonated and deprotonated. We're thinking about the ratio of the population. So it's not that all of the amino acids are carrying that charge, it's just more. As the further away you get from the pKa, the higher the proportion of the conjugate base to the conjugate acid, or vice versa.